كرك يعني أبو قوس، كرك يعني أبو قوس، أبو قوس أبو قوس.
is just such an escape.
It's so peaceful. I love that. You just step away from everything. It makes you feel alive.
كل لحظة سعيدة مهما كانت صغيرة تفرق مع 7 دايز. تكبر ويزيدها وناسة. 7 دايز كروسان يسعد أيامك ويزيدها فلة.
It's just such an escape.
It's so peaceful. I love that. You just step away from everything. It makes you feel alive.
further ado, let us begin our event with our first session of the day.
Start the morning with a speech from a respected academic writer. Please join me in welcoming Dr. Ahmed Al-Mashri. Dr. Ahmed is an associate professor and head of the Department of Electrical and Computer Engineering at Sultan Qaboos University. Dr. Ahmed is the current chair of the IEEE Oman section. Dr. Ahmed will share insights on a sustainable Oman for the next generation, the role of academia in teaching. It's our honorable speaker. A round of applause.
So, alaikum. I hope everyone can hear me back. It's really a pleasure for me and an honor to be here. I tried to be here yesterday. Unfortunately, I couldn't because of work commitments. But I was able to attend part of the events through the YouTube broadcast channel. I enjoyed attending part of the talk about game theory. To be honest, this is not really my area. I usually give technical talks. But then Dr. Naga gave me a challenging task. He said, I want you to talk in the following slide is basically collection of thoughts, experiences, and ideas. And probably I'm asking more questions than answering them. So please bear with me. So what I want to do, I'll talk about 4 points, and you will see that at one point there is a lack of boundary between one talking the other. So I want to talk about the kind of volatile world that we have. How is that affecting quiet? How we can actually practice some of the ideas that I've present today. So different ideas, but it's probably not what you have in mind. This is what I mean by. So in 2nd of April, the President of the United States, he made another protectionist act by basically reciprocal tariff. That no one expected what will be happening in the next few days. I don't think even he realized that it's going on. And the results were actually very clear. Markets went down. Until now, the Muscat Stock Exchange, it's actually suffering because of what happened. Even though until now, they were not really effectively enforced, these tariffs. But just when the President of the United States announced that he has the intention, that caused a collapse. And the result that within 7 days, the big top tech companies, they lost about $10 trillion in their market value. And that's a disaster because those $1 trillion took years to build up. For example, NVIDIA, which builds the top AI chips, all what they have accumulated in the last 2-3 years, the boom that they had, they basically lost. And even Apple, they were not actually isolated from what happened. Even Apple have been, sustained some damage because of these tariffs. And the reason I'm showing these slides is that just to show you how things are really vulnerable. And the market is so entangled, and globalization is something that forces that once you have a superpower taking the market in one direction, everybody will. So how is that related, and how is that impact Oman, or at least the region? Since what happened, oil prices went down, and unfortunately, even though we had a 50 years of renaissance, still until today, our economy is actually based on the revenues of oil and gas. And what this means that all of these plans that they had for the next 5 years, probably heard some of the leaks, either been put on hold or they've been canceled altogether, which is basically a very bad news for the not only academia but also industry and the social development in the country. So this is really bad news to everyone. On the other hand, this might pose some opportunities for the Sultanate. Even though we're not really worried by the president, a high reciprocal tariff, ours was only 10%. But that 10% means that we are relatively speaking less than or build factories, and they can export their products to the US with a higher profit margin compared to if they would have produced in the origin country. So there are some vulnerabilities, there are some challenges, but there are also some opportunities. It's just up to the government to seize those opportunities. But the fact is, according to PwC, at the beginning of the year, the plan was and the budget was that 68% of the revenue would come from oil and gas. Now that the price dropped down to $70, this means that we have challenges. And the question is, for how long are we going to continue doing this? When the prices are down, we start talking about sustainability and diversification of economy. When the prices are up, we get this dose of dopamine and then forget about it for the next cycle and so on and so forth. I think something has to happen and we should learn from these lessons. We might recover from this. Nobody knows in the next cycle. Sorry, I forgot to put my phone on now. New dilemma. We keep relying on oil and gas as the main source of revenue, and we're really exposed to the prices of oil and gas. If they are up, we keep working on we keep embarking on these projects for social development, expanding the economy. Once the prices are down, then we have to go to austerity, and then we have to look at different measures to reduce the expenditure of the government. So the whole point is how we can make all of this sustainable. I'm not really a man of economy. I'm a very simple academician who's in engineering discipline. So I'm more of a technical guy, and I've done a number of years in teaching. So what I want to do here is just to share thoughts of how we can invest in sustainable development as academicians. Okay. Many of you, if not all, development goals. So these were announced in 2015. The whole point was by 2030, we would have achieved these development goals. And the top are no poverty, good quality, health, and all of these 17 are supposed to tackle different aspects of development in a nation. But for me, even the SDGs we talk about the 17th SDG, it talks actually about partnership. And actually, we are one of the partners, academicians, and we are expected to contribute to the implementation and to achieve those SDGs nationwide. Now, those who are locals probably are familiar with the diagram. Those who are in our this is new to you. Part on the Vision 24. The whole point is that by 2040 we would have achieved these targets. We have 12 national priorities, and actually these national priorities are nicely mapped to the SDG. And actually in the Vision 2040 document, I think page 43, they have this nice table where they present every task, every national priority, and how it maps directly and indirectly to one or more of the SDGs. So basically, on paper, they are aligned with the worldwide movement. What lacks here is that how can we implement all of this? So what I want to do in the following few slides, I just want to share a few thoughts, and I'm more than happy to discuss more towards the end. First of all, whether we like it or not, the way we conduct lecturing is no longer, I'm trying to think of a very nice word. Probably it's not the best way of engaging with students. The way it's been done right now, at least to the institutions that I've visited and to the professors and educators that I talk to, it's more about, I have some knowledge, I just want to pass it on to the students. And that knowledge is more of classical, traditional, and it probably lacks to discuss global issues. For example, many of classes don't even mention the SDGs, which means that our students, probably they are technically, well, but and that's an issue because eventually they have to, at one point they will graduate, they will be out in the market, and they're expected to participate and contribute to the growth of the economy. So we need to switch from this traditional way of conducting classes, lectures, to something more progressive. So that would be the target. But of course, like everything else, it's easier said than done. How can you actually achieve this? Now, I tried to identify few areas, some of which based on personal experience that I had, some of which I've learned through other colleagues that I have interacted with, and the others, it's based on a little research that I have done in preparation for today's talk. One of which, curriculums have to change. So we have to modernize the curriculum, not only vertically, like we do, even horizontally. The learning environment themselves have to change. They have to be more engaging. We need to have students to participate more, engage more, talk more about what they think of technologies and things that are happening around them. The institutions cannot be isolated of what the things that are happening. We have to align them in terms of regulations, policies, and so on and so forth. And whenever you do a drastic change in an institution, even if it's academic, to see changes there. Things that they have been used to and accustomed to over the last, 10, 15, 20 years. So there has to be a way of monitoring this. And one example is what University of Michigan has done. And then they wanted to monitor how students and even faculty are acclimated to changes. So they keep interacting with the stakeholders, in this case, faculty and students, And through the surveys, they want to see if there's actually any improvement. So you need to close the loop. You make change. Otherwise, whether or not you're actually the change is actually positive or um, it's more important than ever that you have to reach out to industry. I just learned now, and probably it's out of ignorance, that Mr. Ashraf Mamri was the patron of the sermon yesterday. And that's really important that you don't really always rely on VIPs from the government, cabinet, but you also need the industry to be on board. And at least in stuff, with industry, and we asked them of what they think about the graduates, our graduates, the quality graduates. But that's always the nice turn of the event. But across all meetings with industry, technically students are good, but they're lacking some of the skills, which I will talk about in a second. So you have to make sure that you're always reaching out to the industry and you always have some bridge between the academia and industry, because eventually they are the consumers of our products, which is basically the graduates. So the skill sets that they keep talking about, critical thinking, I know this term is roaming around a lot, but I've tried it even in my classes. It's not easy to engage students in critical thinking because students since school, they have been trained to be given all the all the unknowns, and then come up with a heuristic or a mathematical equation to solve. As soon as you take one of the unknowns from the students and ask them to think out of the box, this is where they feel awkward and they feel out of touch. So this is really important that you engage students in critical thinking exercises. You don't really have to give them all the unknowns. Allow them to make assumptions. Very, very important. When they go to industry, there is no chance that whenever they are tackling a problem or a challenge, they will be given all the unknowns because even their bosses don't know all the unknowns. So it's the engineers who are thinking about sustainability and development come up with a making assumptions. Based on those assumptions, they would know learning any communication. I don't know the students of UTAS probably doing better than SPU, but the comment that we get that your students, again, they're good when it comes to uh, problem solving, so they don't know how to market themselves. They don't know how to present their case. Probably it's a fault of the educator because we focus more on knowledge, rather than having the students being engaged in dialogues, discourse, discussing ideas. And that's really important, especially today. Market really requires engineers who can really talk, can really discuss. Another thing is that's really important. You have to discuss, as educators, we have to discuss SDGs even at an early stage. You don't really have to go into the details and make it really complex to students. For example, in Public University, we have one course that all engineering students have to do. It's Introduction to Engineering. That would be a nice spot where you lightly talk about SDGs. Students have this tiny exposure that the globe is trying to think solutions to existing problems. But that's probably not enough. Towards the end, for the graduate, and this is something I'm working on currently, the department I head, is to first encourage, but then it becomes the mandate that students must explain how the problem that they're tackling in their capstone design, or we call it the 5-year project, How is it really tackle one or more technologies? You don't want the students to be in this cocoon, working in isolation, without trying to think globally and figure out how the solution that they're trying to develop will actually address global issue. It's very important that students think globally. Locally, it doesn't really work anymore. Disciplinary is discipline. It's really important, even though it's fluffiness. The thing is, some of the um, inspiration that the Sultanate and other states in the region are working on, worked out about sustainable city. What's the sustainable city? Who's going to do the water treatment? What about the communication? What about the challenges with waste management, waste recycling? These kind of issues cannot really be tackled by a single discipline. You need engineers with different backgrounds. You have a diversity among themselves in terms of background and knowledge and skill set, so they can work out solutions to these problems. You cannot wait until after they graduate for this to happen. It needs to happen their bachelor degree. And that's the thing that we have tried at Sultan Qaboos University by asking or by encouraging students to work at the colleges, allocated a budget for pioneer projects, and that what can release to the product only if they can show that they are working in a multidisciplinary. But that's particularly one way of encouraging students to compete with students from other departments of colleges. Okay. I'm not sure if we have students here today. I see ties and suits and stuff. Not any students here today. Uh, At least a couple of them. Excellent. I'm sure I had more audience from students, and probably what you're about to see, you will not really like much, but I will say it anyway. Uh, Social media has become the go-to information for the access. And what I realized, at least, I don't want to be, you know, I don't want to make it as if I'm generalizing. I'm talking about the students that I teach, the students that I interact with, and also my children. They don't watch news. They don't read books. It's a matter of relying on social media with all its variations to get information. This is really, really risky because number one, social media is basically a bunch of algorithms. It analyzes what you're reading, what you're interested in. They propose more of the thing, and you eventually find yourself in a bubble, even though you don't really realize. So let's probably read about it. Doubling it happens consistently, but gradually. All of the information that you receive is information that you have tendency to believe and accept. And the algorithm make sure that you're not exposed to other kind of information that probably you don't agree with. And probably you've seen it. You watch a couple of YouTube videos or shorts, get more of this thing. You follow a few accounts, Instagram and X, and then you get more of this thing. So algorithms have been made to make you happy, not to make you knowledgeable, not to make you ready for the future challenges. And for students, this is something very, very critical. You have to come up to that problem, be ready to accept facts, new information, that you even agree, but you understand how others are thinking. That's very important for students who are ready for work. Sorry, the other thing is there is a tendency of students to think that if technology is the same as developing it. So when I ask students, what do you think about technology? How are you participating to produce code? You know, find my code. That's not to develop in technology. but basically using a technology, the output of technology, to make your output a little bit better. You have to think of how can I make things better in terms of development. So, for instance, if I use LM, large language model, how can I make them more suited for the issues in Oman? For example, in preserving issues, that's basically customizing tools to make them more adapted, more useful for the country. Say I'm using Gemini to refine my code, that's not really developing the technology, not even contributing to it. Are you contributing because you're giving more data to the algorithms to make themselves more better, but you're not really directly participating in the development of the country. Last but not least, this is what the students really hate for it. You have to book. You know that for some reason reading a book has become something of the past. It's some think of it as a backward thing. I have my iPad. I can access any information. I get excerpts of textbook, read it, but believe me, it's not the same. And reading your course textbook is not reading a book. Reading a book, it means you dedicate time every day, every week, where you read a topic that is extracurricular. You want to expand your knowledge. You want to know more about the topics, macroeconomy, politics, social development, and so on and so forth. I know this is really difficult for students. They don't like to read anymore. But if you want to develop yourself, if you want to be more competitive, so that when you graduate, it'll be easier for you to find a job or start a business, you have to read books. Even entrepreneurs, some of my students who are graduates now and they have opened up businesses. I ask them, what do you do for free time? The answer is always the same. We read books about so and so, which is related to entrepreneurship. So even if you have the entrepreneurship spirit and inclination, you have to expand your horizon. Those are educators. Um, Educators, they've been doing the same for decades now. And I know some of the stuff that I will present right now, even myself, I fail to practice from time to time because it's easier for us to do the same. What I've done yesterday, it's easier for me to do it today and tomorrow. So, first of all, you have to engage more students. This one way of communication is not really working anymore. Think that when you ask a single question and you wait for a simple answer for the student, that's engagement. That's not engagement. That's just Q&A. We have to switch the classroom into not all of it. I understand that you have material that you have to cover, and you don't really have all the time. But you have to dedicate some time in the class for discussions. You want students to be accustomed. You want them to feel comfortable expressing their ideas. Again, it's not because your ultimate goal is to make sure that everything that they say is factual and right. It's just that you want to train them, train them to what will happen after they graduate. When they are in meetings, they're expected to voice their opinion. So they have to voice their opinion clearly with evidence if possible. Probably they'll not be right all the time, but that's not really the point. The point is they are trained to talk their minds in a proper way where others can understand. And also, gamification is something that I've been trying. It's not the same as game theory. I don't want to mix it with with the top game like reading about. Probably I'll present one slide at the end that shows you one way of doing it. Also, you have to be up to date with the trends. So whether you like it or not, our students, they spend a lot of time in WhatsApp, Instagram, and X platform. It's good that from time to time get to and check what are the trends, what people are talking about. Pivot point that your students is not going to sleep, you can wake them up by going into one of these hot topics on the trends and use it to your benefit. Again, you just want to engage them. You want to be more attentive. Probably I already covered that. Question? I don't see. 0 minutes. I don't have 50 minutes. I'll speed up. Okay, very quickly. Um, minute. First, I was hesitant to use it, but one of my colleagues, he really encouraged me that I tried. You see, the dynamic inside the classroom is completely different. So, okay, with fine. What it is that I told students that if you participate in this class, you get extra points. It's bonus, so something extra. And the way we do it is that I'll topic, then and tell them, okay, it's your time now to discuss and answer questions. And I had to hide the ID numbers of the students just to, for confidentiality. But the response and the reaction to me, it was really surprising. Possibly surprising. Told me. I could feel that suddenly they are more attentive. So these are simple tools that you can use. This tool, it's the entry level is free. You don't really have to pay anything. But if you want to keep records of your students, if you want to export results, Excel, then you have to pay money annually. So it's something that I highly recommend. I know that I'm out of time, but I really want to tell you this story. I'm sure that you are familiar with the logo on the left. Yes. Are you familiar with the logo on the right? Maybe not all of you. So let me tell you a story that it happened in the early 2000s. Back then, Netflix was in its middle. It was founded in 1976. So John Anticchio, he was the CEO of Netflix. And their business model was completely different from today. If you want to hire, rent a movie, you go to Blockbuster, you get your VHS video for 2 days. Late or everyday delay, you pay extra fee. So very simple model, business model. It worked for decades. So John Anticchio, who was the CEO, he went to the board of directors and he told them time has changed. We're seeing a phase shift. We can no longer rely on the regular traditional business model. We need to move into digitalization. Basically, we need to move to streaming. So Blockbuster total streaming at the same time when Netflix was doing its first attempts. What do you think the response of the board of directors? Yes or no? Of course, otherwise we're not presenting this slide today. They said no. Do you know why they said no? They said 15% of our revenues, it's because of the delay in returning the DVD. So we want to stick to the same. John Anticchio resigned. In 2010, Blockbuster announced the bankruptcy. Within 6-7 years, they lost business because they were fixed on that 15%. They couldn't see the billions of dollars that they achieved just by switching to streaming, just by switching to digital. Today, Netflix is not only a streaming platform, Netflix is actually producing movies. Probably you've seen some of the titles, produced, or a Netflix movie, Netflix series, Netflix comedy. So I don't know if you like this story or not, but this is one of that I tell my students during classes. One, I get their attention, and I hope I got your attention as well. I want to tell them about the past, present, and future, and how the trends are moving. The issue is that students don't like history. So I avoid telling that I'm telling them a historical story. I show them logos of something that they like, and then I tell them a story. Entrepreneurship, sorry about the crooked entrepreneurship. So when you tell them about the trends and how you can open a business and how you see the curve ahead of everyone else, and therefore you can open up your business with in the region, that probably instigates that entrepreneurship spirit in the students. Also, you want students to always remember that if you don't evolve, you will devolve. It doesn't matter if you are Blockbuster or DEC, if you still remember that company long time ago, or Nokia, for example. If you don't evolve, you will devolve. And that's what's basically the essence of sustainability. Last but not least, once I tell the students this story, I give them time, 5, just for them to exchange ideas. What do you think about this story? So that gives them time to reflect and participate. Sorry for taking more, a few more minutes than what's been allocated to me. I'm very happy again to be here, and I hope that you like this presentation. Jazakumullah khair. Thank you. الحين I don't know who is the moderator today. Any moderator? Do we take questions now or later? Later. Thank you.
Thank you, Dr. Ahmed, for that enlightening and future-focused keynote address. Your words have set the tone for today's discussion and have certainly inspired us all. To honor our keynote speaker, may we call on stage Dr. Malik Al-Zakwani, WTFS Vice Chancellor for Postgraduate Studies, Scientific Research and Innovation at UTAS Al-Musana'a. Dr. Nihad Az-Zajali, Deputy of Assistant Vice Chancellor for Academic Affairs, and Dr. Nasser Al-Hadabi, Department Head of Engineering, UTASA. Please come on.
May call Dr. Ahmed Al-Bashri on honoring.
Next, we are privileged to hear from a global expert in solar energy research. Please welcome Dr. Muhammad Adib Ibrahim. Dr. Muhammad is an associate professor and the director of the Solar Energy Research Institute at the University Kembasan, Malaysia. His research areas are solar cells, biophotovoltaic cells, nanostructural materials, energy management and conservation. Today, Dr. Muhammad will be presenting a talk titled Recent Developments for Process Materials for a Solar Photovoltaic Application. Please, let's give a big round of applause to our distinct
Can you use the point? Yeah. Okay.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I'm glad to be present today. Thank you very much for inviting UTAS top management of UTAS Musana to invite me as one of the keynote speakers today. So today, I would like to share my progress of my research. This will be the finding so far has been progressing, has been work related to the solar photovoltaic. What we know that today, the research of this on third generation related to the emerging solar cell on the perovskite solar cell. But today, we'd like to talk about on the perovskite material. I believe this, even though the structure is ABX3, but generally it can be expanding application in the optoelectronic application. Only solar cell, other than that. So today, I'd like to share a bit of my knowledge. Then I'd like to share about the finding of my research. My team in the what we can see here today, the university has been established with the various achievements, and even in the top 200 in the QS ranking. You can see UCAM has been located in 3 places in campus, but recently in this last year, we have been established 1 branch in Qatar. So this will be the international campus. It's been placed in Qatar. This will be a new benchmark of the university. So without any delay, a bit on the introduction about Solar Energy Research Institute. What we can see here, SRI has been established in 1st July 2005. But today, this year, we're going to be celebrate our 20 years anniversary, inshallah, in July. So this will be the some facility what we have. We have some brochure has been placed in the booth there. If you would be interested related to what we have, some facility that been present in our lab. This institute has the only institution have complete facility in terms of solar cell laboratory and also solar thermal laboratory, which is enhancing on the research on the solar photovoltaic as well as the solar thermal. Then also we have related to the architecture on low energy architecture, as well as we do study on social impact, and for those others on the related to the energy material laboratory. So as what you know today, okay, directly to the what we've been topic today on the name of perovskite. So perovskite is a name as we can see here the oxide of material calcium trigenite. So what we can see originally has been found by Russian researcher in 1839, but we can see here this development of this structure has been shown progressing in last 10 years. We can see the progress of this research on the perovskite has been grow rapidly compared to the development of silicon solar cells. Take about 50 years in order to get the maturity of the cell. But we can see here the crystal of structure of this perovskite shows the body of consisting of 3D ferritic long range or ring of atom, ion, and molecule. So we can see this structure showing complexity of this material, but it can be expanding in different structure. Then you can see that the lattice point, the unit cell, can be a different lattice of the structure of the cell, can be in different form, either in a monoclinic, orthohombic, or tetragonal, and other type of structure. So we can see here some. What is a perovskite structure? It's representing of the ABX3, which is representing of A plus 2, representing of, it can be calcium or strontium or La or Y. And B can be others and structure like titanium, ferrum, and others. But it can be formed in the different either organic or so in inorganic structure. When X2 minus 2 representing either can be oxygen or can be a halogen material like chloride, or bromide or iodide. Okay, depression of the structure. We can see here it can be, as I've been informed, on the orthorhombic structure or the cubic structure can be formed either in this structure of formation. But this will be the if you do on research on the FT, you may determine on full structure of formation of this formulation, but it depending what kind of application you like to use. But the way of this formation can be formed it can be form of the structure due to distortion. Either it can be due to the size of difference between the cation or A as well as the B side, and this distortion can be play the important role as a property of the material. Either it can be a hexagonal, tetragonal, cubic, and others of other type of material. But this material is presenting of inorganic material, what you can see in the slide. But in terms of this application, has been done in the different application what we did in our lab in the different form. Okay, this will be the some type. It's related to the structure. What you can see here, it can be formed structure as can see the perovskite layer as you see based on the calcium. Either it can be strontium or either can be a bismuth based material. But this will be the expanding material or structure can be formed if you based on this formation. All right, if you can see here, the general application of perovskite can be beyond on the solar cell, or it can be applied as a sensor, thermoelectric material, laser, catalyst, battery, as also a fuel cell. But today, I would like to share some information or my finding related to the application on the solar cell. So some application on the related to the energy material as well. But generally, we can see application, for example, the working principle of perovskite solar cell. So this will be the structure, what you can see, formation of the glass, ITO, ETM, electron transport layer of material ETL, and perovskite material also HTL and the contact. Then this will be the structure, how the works of electron and hole, which is can see upon of the light absorption, then the electron has been moved to the electron side, and also the hole going to be on the positive side. So some material has been used. What you can see here, the metal contact, sometimes they can use gold, platinum, silver, and then can be on the copper as well. But for the hole, beyond that, it can be a spiral, then other like PTHT, and also on the first absorber layer, representing of structure of methyl ammonium lead iodide. This will be the general form of the material which is performing in terms of efficiency most higher so far at this moment. For the ETL material, can be representing of titanium oxide, tin oxide, or can be for other structure of perovskite as well. And the formation of lead iodide can be formed different as well. Either can be based on the lead iodide, it can be tin iodide, can be lead bromide, or can be lead chloride. This will be, can be changed in terms of formation of the material. You can see here, this will be the different type structure can be done on the perovskite. Either it can form in terms of mesoporous perovskite solar cell, and secondly, related to the planar perovskite, or it can be inverted. Meaning inverted, you can be reverse direction, then the direction of the light still remain the same. So meaning the structure can be changed. You can see B and C, HTL can be changed at the bottom, and then ETL can change at the top. This will be the variation of the structure can be done in the perovskite solar cell. But this will be as a general information for you. The formation of this structure can performing in terms of the generate of electricity. Okay, generally, ladies and gentlemen, we can see here when we zoom closely to the structure, we can see this will be the some material has been used in the generally of perovskite solar cell. But we can see here the material can be changed differently, but it can be applied in a case of how the material of perovskite can be applied in the general of perovskite solar cell. So for today, I would like to share some information on the research has been done on the FTO, and secondly on the absorber layer of the material. So we can see some material has been applied, but for today, we'd like to some achievement has been done directly for our research. So firstly, on the substitute of FTO, we do on the transparent conductive oxide. What is this? It's a almost media layer representing either can be used as a glass or can be used as a flexible material. This will be the we call as TCO, right? All right. This will be a transparent film has been used as a main layer exposed to the light. So means that the first layer to be absorbed by the light is by using TCO material. So this will be the sort of material must be have features of high optical transparency, allow light to pass through the active layer without unwanted absorption. So this will be the have in the market today is we know about on the tin oxide IO. Second active material can be fluoride tin oxide FTO, but this will be the general commercial as in the market. Okay, this will be the sometime has been used in the TCF, or we can use as a TCO, but we also have some option of research on perovskite TCO as we do research currently. Either can be a standard base or standard based material. All right. What has been done on this progress of my research has been representing on the nickel zinc tin stannite. So we use this material as a general material when you do some doping using a nickel. So this will be the some application has been done. What we do based by doing a doping on zinc tin stannite. So reason is we do doping to improve the property of that material. Okay. So what we done, use of kind of methodology by using AACVD, aerosol assisted chemical vapor deposition, by using in the laboratory method. Even though it's not, this method is much more flexible, but versatile, as well as most method being used without using the commercial of CVD. Often what has been done, you can see any shopping mall has been, even at house, we use aerosol purpose, right? This would be one way to do experimental. So we use this when we use the heater, and also the substrate place the glass on the top of the heater, and then we heat up at the 400 degrees Celsius. So this would be the one way, the cheaper way to do of experimental. So this will be the some result representing of zinc tin stannite. So representing of SRD, and also some result of by using the doping from 0 to 10% of nickel. So there we can see some structure presenting of the, it can be formation of structure formally formed on the when presenting so you can see here the most is with some result in morphology analysis where the film is homogeneous on the layer. Then we can see the grain size, roughness of the material on the doping on the glass substrate. So we do some different in terms of ratio of doping from 0 to 10. Okay. We can see here the optical property. When we do most one of the criteria for the FTO for TCO material to be classified. So we need to determine the band gap. So the band gap should be higher to allow the light to absorb the more large region. So when we do, we can see band gap as we appear. We range from 3.9 up to 4.5. So we can see here the transparency is more than 70%. Okay. Then we can see the electrical criteria of CVD. We may observe the 2% and 4% shows more viable, what we can see compare with the other doping. So we can see here by using the doping itself, we observe 2% and 4% showing the best in terms of resistivity, and also electrical resistivity. Then we also compare with the FTO, which is used as a standard, as the shows in the chart. So you can see here, that show the TCO has been used as a one of the alternative for material to be applied. So the result showing the more comparable and compared to the future. Secondly, the research done on ink as used earlier, where we use system iodide by using the flow continuous flow reactor by producing the ink. So this ink, one way to replace of the lead-based material, which is representing of lead-free in the solar cell, perovskite solar cell. This will be the structure by using the hot injection, or we use a ligand-assisted reprecipitation. So this will be the some result that is shown in terms of efficiency. This will be the step by using our solar cell to fabricate from the ETL formation. Then we use the spin coating as well up to we may have the device of the cell. So we may observe okay. We may form into different perovskite ink. By using of the structure of the device, we manage to have efficiency about which is much more higher than the world so far on this base material, about 3%. This will be our achievement when this structure of the cell has been formed in the size of 1 times 1 centimeter square. So this will be the fabricate of cesium bismuth iodide. Then some result we also show presenting on the okay, we can see also when you do the IV curve characteristic, we can see the efficiency has been shown much higher, 6.9%. So this will be what we plan to filing in terms of patent because it has been reported in the literature so far about 3% only based on cesium bismuth material. So this will be our achievement, which is if you compare with the lead base, it's much more higher, but we know that the lead material is a toxic. So we may offer this as an alternative material, which is our future of the cell. So thirdly, we do on the research on the Ma tin iodide by using a different method, tin-based material. So this will be some different of material, but the problem of this material is stability, which is not stable when it's been exposed to the air. So this will be quite challenging to us, but we are progressing to find the best solution in order to solve of this issue. So we do using of the ligand, then we do some property measurement by using a Raman, where this Raman to show reaction time has been shown in order to mix of these two material. So this will be some solvent has been applied in order to form of this material. So the method of fabrication has been done similarly by changing the difference is by replacing of the adsorbent layer by Ma tin iodide. So this will be some structure has been formed in order to get of the cell. So we still use the spin coating, the facility what we have. Then this will be some measurement has been done. We can observe this when we switching the different material based bismuth to the tin. We may observe the efficiencies slightly different, but the purpose is what we're looking at some option related to the different base other than material than lead. So that's why we may see some comparison result may be shown today, but this will be our lab achievement. So we are progressing to improve. Inshallah, we may see some improvement in later. So this will be the form of the structure of perovskite has been shown small size. Even though its size is 1x1, every layer of this round shape is representing of 0.07 centimeter square. So, right. There will be some progress what we done. Just to get to know you as a conclusion of this finding, to show this will be some achievement of what we done in our lab. Any material or any technology has been done have some disadvantage. So we can see here when we explore new material, we may gain some knowledge on that development of material. So we see here perovskite has been shown some achievement in the last 10 years. We hoping that this will be the one of solution to get to achieve of the SDG, because SDG 7 representing of affordable and clean energy. This will be the perovskite to be alternative or solution to replace of the silicon. What we can see here today has been in the market almost 50 years, where we can see the cell itself can be sustained, can be used up to 20 years to 25 years. But the perovskite is still not reached there. But we believe that all the researchers in worldwide today have been looking solution to improve of this state of problem. Inshallah, we may find, and then we can see this future of the cell shall be used. Okay, I believe that will be my talk today. Hopefully you have any interest of this research. This will be some achievement what we done, research has been carried out until today. So hopefully anyone, you can take some brochure in our booth. Thank you very much.
Thank you, Dr. Mohammed, for your clear and inspiring talk on the future of solar technology. We truly appreciate your valuable contribution to this conference. The floor is now open for questions. Anyone from our guests may ask questions to our honorable keynote speakers, Dr. Ahmed and Dr. Mohammed. Please, anyone can ask any questions now.
Assalamu alaikum. This is to Dr. Mohammed. What is the efficiency of these perovskite solar cells when compared to the conventional dye-sensitized solar cells? Have you compared?
Okay, what we can see here today, the highest achievement of perovskite today, about 24.5% for commercial for perovskite solar cell achievement so far. But compared to the dye-sensitized solar cell, the highest achievement is 13%. It's quite low, but there's no progress of the dye-sensitized solar cell until today. but we can see here almost of the researcher has been progressing research on the perovskite solar cell progressing until today. Thank you.
Thank you. Also, one question. You used glass substrates for these fabrications, right? Have you tried any other substrate other than glass which may improve the efficiency?
Repeat again.
You used glass substrates for the fabrication, right? Glass substrates.
Okay.
Any other possible substrates you can use for increasing the efficiency of your analysis? And also one more question. What about the film size? Any analysis on the film size for the different materials you have tried?
Okay. So far, commercially, the most efficiency, as I mentioned, about 24.5% based on the glass. Normally, has been used commercially ITO or FTO. But there is another option to use the flexible PN ITO. Also can be used as a flexible material, plastic based. But the performance is a bit lower compared to the glass. This will be another achievement for the flexible. The research is still ongoing. The percentage of the flexible is about 10 to 12%, half than the glass substrate base. Does it answer your question? Is there others? Yes.
Assalamu alaikum, Professor Muhammad Adib. I have one question for you and another question for Dr. Muhammad. For you, Doctor, as you are the director of Solar Energy Institute in UKM, has any research produced by your center been commercialized or not? This is the question for you, Professor. There is another question for Dr. Ahmed. Many of us are using the traditional way of teaching. Even myself, I'm using the traditional way of teaching. What are the risks related to keep this way of teaching and not make any changes in it? Is there any risk? Thank you very much.
Okay, I'll just answer. The question related to the research on the commercial of the solar. So we, on the perovskite itself, we have research grant from industry. But industry from our local industry, which is looking at the local talent on the development of perovskite solar cell. But in terms of commercial, we are still a long way to go. So we need some collaboration international, because currently, for your information, the perovskite solar cell, solar panel has not been commercial yet. Everyone looking to commercial this product, but it's not in the market. So everyone has been keeping all the secret how they've been developed of the panel of perovskite. So this will be the challenge to us to get high, big talent. But you can see here today, even in the internet has been shown, like Oxford PV has been produced a large scale of the perovskite solar panel. This will be the challenge to us for the small institution like us. So we looking for international collaboration to enhance, to make the commercial can be happen in one, inshallah, in one day. Can I answer your question? Thank you.
So to answer the question, a couple of things I have to touch on. Number one, there used to be a classical study showing that the student attention span is about 20 minutes. So if class starts at 10, you would know at least they will last until 10:20 before they go into sleep mode. After what happened in Corona, And with the excessive use of social media, students' brain have been accustomed to short span. So now what we notice that it goes down to 5 minutes. So 10:05, they're out. They're looking around, they're not really with you. So that's number one. Number two, the requirements of the industry mandates that you have to go into soft skills. So given that we produce graduates for the industry and they are the beneficiaries, we have to listen. So it goes beyond missing the opportunity. It's a matter of if we don't change the way classes are being set up, then our graduates will not be competitive compared to the other to their peers, whether locally or regionally. So I'm not trying to say that we will all switch how we conduct classes, 180 degrees. No, I think it should be done gradual. You can try a few techniques. Probably you could start with few minutes, because if you do drastic changes, it will be very difficult for you to measure what went right, what went wrong, because that's what you do as educator. You try an experiment, and then you wait for some time until you see the results. So what you can do, you can make incremental changes, monitor the progress, and if things are going well, you can do more of the same. If not, then you have to go back, rethink, and then try something else. So we have to do it, but we should not do it drastically. It should be done gradually. Shukran.
Thank you. Thank you.
Okay, thank you, Dr. Mohammed and Dr. Ahmed, for your valuable answers. We will now take a short refreshments break. Please enjoy the refreshment available in the auditorium area. We'll resume shortly in 15 minutes. Thank you.
begin the next session.
Is an expert in advanced manufacturing and laser technology. Please welcome Dr. Mohammed Y. Ahmed Ubaidi. Dr. Mohammed is a design engineer at NAMO Ireland Ltd. He is also an assistant professor at Dublin City University and funded investigator at the IFORM Advanced Manufacturing Research Centre Ireland. Dr. Mohammed will be speaking on sustainability and recent advancement in laser-related manufacturing technologies, a case study on additive manufacturing. Let us give a warm welcome to Dr. Mohammed.
Thank you. Assalamu alaikum. What are you please ignore that can start in 10 minutes late, so I'm looking for some compensation, please. So the sustainability and the recent development in laser technologies, and the focus will be on additive manufacturing as a case study. Starting with definition for those who have no experience in additive manufacturing. Additive manufacturing, as defined by ICSDET, the American Society for Testing and Materials, is the process to manufacture a part, usually by adding materials layer by layer until we have the full 3D part. And this definition distinguishes between the traditional method in manufacturing, like in lathe machines, milling machines, in which we start with a bigger part and then we start subtracting materials to achieve the final part design and requirement. The technology, additive manufacturing, is classified in 7 categories, either based on the medium used to cure the material, whether it's laser, UV, or like in binder jet, some chemical binding maybe, or also can be classified based on the material used. Is it metal? Is it polymer? And so on. So the focus today will be on number 6, the powder bed fusion, just to save the time. This is a very good example of a typical additive manufacturing lab that we have at Dublin City University in Ireland. The machine here is made by a community from Aachen, Germany. As you can see here, can you still hear me? So the printer is this body here, and the build chamber is there. The computer and the gas control software is uploaded into this cabinet here. We start the process by designing our part on our own laptop or personal computer using any CAD software such as SolidWorks, Creo, Fusion 360, and then save it in the format that the printer can understand it and read it. On the printer, we slice this part into slices by defined layer thickness. Usually here, like opposite to FDM or WAM, wire additive manufacturing, the layer thickness here is in micro scales. So start, for example, from 10 microns. and can go maybe up to 200 microns, depending on the powder particle size, depending on the laser power. You can control the layer thickness. The printing process here, because we are using lasers, so we have to work in inert gas conditions. Here we use argon. Number one, to avoid oxidation, but very important, these powders, metal powders, are inflammable, explosive, and also oxidized. So we have to work in inert gas conditions. We use argon or nitrogen here. When the curing beam is electron beam, the whole process is work under vacuum, high vacuum. Again, these metal powders are explosive and inflammable because of the mass to surface area ratio. Some metal powders, for example, magnesium, can cut fire if you hold it by your hand from your body temperature. So that's why when we handle the powder, we store them here in a fire retard storage, 90 minutes fire retard, and then we transfer them from the export containers, big containers, to smaller containers, and then again, inert gas conditions, glove box. And then we load it to the printer. Just in case of any leakage, and we have argon to avoid suffocation. We have oxygen sensors installed around the machine just for the safety of the operator. Here you're going to see some video. This is the build chamber, which was the build chamber which I showed in the previous slide. This here, where the part is being printed, the laser comes from the top, through an optical cable. And then part number 2 is the 3D scanner, which translates your CAD file into 2D, where the laser melts the powder. This is the powder storage here. And part number 3, the orange part, is the powder recoater, which moves left and right to supply the powder on the build plate. So here I designed this lattice structure using SolidWorks. Then, as I said, I will save it in the format that the machine can understand, which is .stl. This is the slicing software that the machine has. And here the laser beam is coming from the top, actually, top window, which is there, and melts the powder in selected positions based on your CAD file. That's why the old name of the process was selective laser melting, SLM. Now it's known as laser powder bed fusion if we are using laser, and electron beam, EB, PBF, if we are using electron beam. Some of the features of the process, we can print very complex geometry. That's very, very important. Like this heat exchanger, it's actually very small. The bigger dimension of this heat exchanger from here to there is 25 millimeters. And you can see 2 fluids comes inside from here. This is one hall. This is a cross section of the heat exchanger. 2 fluids enter from here and then exit the heat exchanger from the top. And another fluid for cooling comes into here and then. So you can see the geometry. This is a coil in this geometry. And you can see the pins, how complicated they are. There's no way to manufacture such part in traditional methods. And this heat exchanger may replace a heat exchanger of this size. Number 2, these are different materials. This is copper, stainless steel, Ti-64, which is titanium, 6 aluminum, 4 vanadium, and nickel titanium. these materials, especially titanium alloys, are very brittle. When you machine them, a lot of tool wear you will have. So we don't have tools here, no tool wear. Number two, when you come to this is 300 micron diameter, each wire of them. They cannot stand the cutting and mechanical forces of the milling machine. Even if you inject them in injection molding, maybe you can do this part, but there's no way you can do this part. Imagine this part, when it was printed, it was sliced. So in each layer, the laser melts wherever this selective locations. So material difficult to machine, we can do them here, and complex geometry. The rest of the benefits and sustainable features are here. I won't go through all of them, but I mentioned in terms of material flexibility, the top slides there show you a good combination of the available and printable material. Minimal material waste. So you can see in the second picture there, this is impeller of a turbine or a pump maybe, made of stainless steel. All the powder around it will be reused like you saw in the video when I was removing the powder with the brush. So all the powder around it will be reused multiple times before it's recycled. So still you recycle it. During the reuse, you may sieve just to get rid of some affected particles, and you can mix with fresh powder if you like. Usually biomedical companies use 100% fresh powder, so they don't recycle. The last figure is the traditional method milling, and you can see the swarf and the chips. These are all have to go to recycle. No tool wear, and we have automation. The process is computerized, so it can be fully automated. And this meets the SDG goals indicators, which Dr. Ahmed mentioned, listed by the United Nations, because the machine is, again, can be fully automated. And one of the goals of the United Nations that we have to achieve, hopefully by 2030, is to readdress the human role in manufacturing, to avoid error, or any human error and material wastage. Significant energy saving. You know, most laser systems are plugged to wall, but the output energy is way higher. A 1 kilowatt fiber, like what laser here we use in our machine is only 200 watt. Some machines have 1 kilowatt, and this can bite and melt any metallic or ceramic material. And last point here, this is very useful actually in repair of material. So like I saw a factory in Ireland for Lufthansa, they repair the damaged turbine blades. So whatever the wear is, they machine it, achieve like flattable, and then they rebuild on top of it. So it can be used in repairing also, repairing damaged parts. Sorry, it's not moving. Next slide. That's the back here of the next. Yeah. In terms of sustainability, several researchers published like the sustainability of the technology. Some of them focus on one specific part, or use it by using two methods, the traditional and the additive manufacturing, and compare the price. Some compared the different machines, different categories to produce one part, and then they reflected against the cost. The highlighted one is our research, published last year. In this research, I produced one part. They were testing samples, of course. by using different layer thicknesses. My aim is to say, instead of I print the part using 30 microns, I will print it using 60 or 90 microns. So I will save the time and consumables also, which is the gas and everything, all the energy also. I selected nickel titanium here because nickel titanium is known as a smart material. It can be a shape memory alloy widely used in biomedical and aerospace industry. And it can also be with very small change in the nickel content. It can convert its properties from shape memory into superelastic. And that's a different application. And it can be not biocompatible. So that's why I selected nickel titanium, because these two metals, I'm melting them here using the laser. So in order to melt titanium, some of the nickel is vaporized and sublimated already. And that will change, like from 50% atom weight percentage is a shape memory. If the titanium is 51%, that's superelastic. And it can be not biocompatible anymore if titanium changes its phase from alpha to beta. So that's why I selected nickel titanium. And I was my output measure was two things: density. My goal is to achieve the higher density, closer to the full density, so that I can say, okay, it's close to the cast material. And number two is the chemical composition. Again, once I melt material, I want to maintain the chemical composition as the raw material, which is the powder. So here I calculated the time, and I find the correlation between the time and the build layer thickness. So in future, I only use this correlation to estimate the printing time. I used three different layer thicknesses: 30, 60, and 90 microns. Usually we use the volumetric energy density because we are using power. And these three very important variables: the scanning speed, the layer thickness, and the hatch space, which is the distance between two consecutive tracks of the laser beam. And then I calculated the density. So in blue, these are the 90 microns layer thickness with these volumetric energy densities, and then 60 and 30 microns. My aim is to achieve the maximum density. I found, working with this VED, I got this density, which is very close to the 30 microns. Then I took only these samples to further testings: mechanical properties, chemical composition, phase composition, and so on. So this was promising sample. In terms of the surface, usually we have very high surface roughness. I will come to the reason why is that. Like when we mill or lathe machine, you expect the surface roughness is in the range of 3 or 5 microns. But here very often we go a bit more than 25 microns surface roughness. And if it's EB, not laser, it's more than 50 or 70. So definitely you need post-processing to enhance the surface profile and surface quality. So I got the 90 microns with that surface roughness. SA is relative to, or alternative to RA. RA is the average surface roughness in 2D. But here I'm taking area. So this is the surface roughness in 3D. So that's why it's SA. And it's more significant and scientific term to use. So the surface roughness was very close to each other, which means the same post-process to polish is required. So there's no drawback here. And then the saving in build time is this much for the 90 compared to that much for the 30, and the energy saving on the machine. Then I tested the chemical composition, as I said, and everything. These are all some of the features of the process, but that doesn't mean it's perfect process. it has lots of defects and challenges and weaknesses we have to overcome. Number one is post-process. You have to do post-process after additive manufacturing, especially for biomedical and aerospace parts. I will give you an example. So when you print a dental implant, surface roughness is good. It's not bad. But here it's random. We need it controlled. I need to say, I need this much of surface roughness. So, like for example, in dentistry, we have 3 levels of different surface roughnesses in one implant. For the bone growth and gripping, we will be looking in the range of 20 microns. Above that, for the protein growth, we'll be looking into 5 microns. So the best solution is to post-process the part after printing, polish it, and then re-roughen it, which is called texturing. So I apply texture that I need. The other drawback actually is the non-isotropic, as Dr. Saad mentioned yesterday. The process is not isotropic. This pin here, for example, was printed in this direction, bottom to top. When we start printing, it's room temperature on the build plate and the powder. As we proceed with printing, with every layer, we are adding more thermal energy. So the top has larger grain size in the microstructure compared to the bottom. The bottom is higher strength than the top. So this was just a pin of 10 millimeter diameter, 60 millimeter length. I sliced it just to prove and measure the stresses, residual stresses, thermal residual stresses. While I sliced it using the wire EDM, the sample was diverging like that. And that's the function or indication of anisotropic stresses inside the part. Here, more stresses than there because of the high cooling rate. The surrounding here is still cold, but the surrounding there and the mass of the part itself is being bigger and bigger, so it can store more heat. So there was less thermal stresses on top. Also, the layer thickness increases the temperature, even if you are using the same processing parameter. This is the 90 microns, higher temperature than this, based on this scale here. Please only use the colors to check, because this is not a temperature. This is a function of the temperature. We have the thermal sensors measure the temperature in millivolts. So these are millivolts. The reason why temperature is higher in higher layer thicknesses is that we put more powder already because the layer is thicker. And there is gaps between these particles. Gaps or gas gaps are like thermal insulators and so on. So these are the temperature. I will show how we measure them. In one layer, see the difference in temperature. This is the laser scanning direction and laser progressing direction. So we scan in a zigzag way, left, right, to here. So we start from low temperature to very higher temperature here. On a normalized scale is over 40%. And that's like massive weakness, let's say. The microstructure, see how big is this the grain here compared to here, which is this area here. Larger grain here because of the lower cooling rate, smaller grain size here, and that's in one layer. The post-process here to achieve or to overcome this problem is by heat treatment and annealing. Sometimes we find porosity like this or larger, this here. The post-process for that to achieve it is called HIP, hot isostatic press, in which we put the part in a high pressure chamber, apply high gas pressure, like more than 700 or 800 bars, with high temperature. And that reduces the internal density inside the part. Sorry, it's good maybe to mention in the previous slide, please. This is It's okay. Yeah, it's okay. I'll keep going just to save the time. It's gone now. Yeah, thank you. So during the print, why do we have surface roughness? Say I printed the first layer, number n, and then proceed to the top. Imagine this part is a feature in a mechanical part. This can be like a cross-section of a tube. So this is the outer diameter, and this is the inner diameter. That part, the pyramid, how do I print it? It's like that. So we print layers, and as we proceed, we make the layers different in length. So one layer is shorter than the other one, and here it's longer because it's a tube. But this is in micro scale, so it's invisible. You won't see it by the naked eye, but only under the microscope. But still, this can be a big drawback. Imagine this is a biomedical implant, and these points here, the corners, can be stagnation points. And it's very good reason for the growth of bad bacteria, and then cause the failure of the implant and big problems for the patient. So how did this happen? So when the laser beam start from here and then move to there, with reference to the previous layer, because it's shorter, we have this roughness which is called stair steps. That's number one reason of the roughness. Number two, we have powder surrounding it everywhere. Powder here, there. When the laser beam come here and stop at this point, based on the CAD file and the dimensions, this is molten material here. And this is still powder that I don't need it. And there will be like micro welding between them. This process called sintering. So I have to get rid of these particles, the sintered particles, and the stair steps. If your part is bulky and can stand the abrasive and mechanical polishing, you can still do the very regular mechanical polishing. It's like any other part. But if it's like stents or lattice structure, complex geometry, or maybe very thin sections, they cannot stand the polishing and mechanical forces. So you can still do electrochemical polishing. And it's very significant because it can polish the inner cavities. Laser polishing, and we have very good experience with that. So you can compare the top surface after printing, after polishing, before polishing. This is the modified and polished layer. You see these stair steps here, which is there and there. I melted the particles and relocate them from the top high peaks to the lower valleys. And then at the end, that is the cross-sectional of that cylinder that you saw. Came like this after polishing on the same magnification scale. The process is here. So this is a different laser. So that's after printing. We finished with the printing. And here I'm polishing. The processing parameters here, of course, the laser power, how much power output, the scanning speed, which is rotational and linear. The sample is made from left to right, and the laser beam is fixed. So the laser power, rotational speed, linear speed, and then the number of passes. So I'm going to repeat the same pass again, and you will see the difference after the second one. So I'll keep repeating polishing until no more optimization and improvement, then I stop. See the second pass, how did it work? And here I can bring the surface roughness from 25, 30, 40, whatever it is. Usually we achieve results between 3 and 5 microns after polishing. At the end, the part should look like this. I'm going to skip some of the slides now because, yeah, this is another challenge here actually. This is a very good paper and very good research, I think, from 2017, yes. Yeah. So this is high-speed camera, and then the speed was lowered down. So when you see this is from the top, the laser beam is coming from the top here, from the side. You can see, like, during the movement of the laser beam, there will be melting, evaporation, so it will generate negative pressure on the top, and this will suck, like make turbulence, and suck the powder, see here, even this powder before the propagation of, see, most of this powder is pushed upward. It was more clear in that video. And then they reside again here on the same part. So when I print the next layer, this will give me defects, either porosity or some defects that will show very low fatigue strength. And I don't need that. There is techniques can be done to eliminate it, but not to avoid it, to reduce this effect, but not to avoid it. One of them is to supply more powder. So if I'm printing in 90 microns, I supply powder enough for like at least twice that, so 180 microns. But the layer is already adjusted to 90 microns, and the mechanism will push them away. Yeah, and then I can also avoid it by optimizing the gas flow rate. Very good to mention, guys, here. And I really advise the academics and the staff in the university to consider this option. As you saw, the process is not easy. It's not straightforward. All sponsors are not allowed to go to the lab for health and safety because they may create this how the particle is. And you can go with the bloodstream and right in the eye or brain and so on. You don't need that. So for our students, and the first few years when we have this, we were in the classroom, and then we take only the students going to be involved in the process, training them before they have the full license and use the. And the first they use it, they have to be sponsored until we assure that they are okay. So I have some fund remaining. Not that I purchased these, but they owned by Facebook. The other option will be Microsoft headsets, which is called HoloLens. Yeah. So I bought them, and then I hired the company, American company. They did the software. I sent them videos, pictures, and all my requirements. And they designed the software. You will see in the next slide. They designed the software and the full lab. So our student, this was the first time they experienced it. They were doing the build based on instructions. When they turn left or right, they find instructions what to do, how to do it with pictures. And then they do the full printing process. This is very flexible because some of our students do the course remotely, and we post the headset for them. So far, thank God, they are sending them back. Hopefully they will. And they do their assignment and their training at home or wherever from their work. And then I still have some money remaining. So I uploaded mechanical testing like fatigue, tensile, compression, bending, impact testing in the same headset. So you have options, which lab do you want to do? And these other chemical etching, chemical processing, and like scanning, electron microscope, optical microscope, electron backscatter, spectroscopy, and EDS. This is very good to train the students on. The last slide, please. So here the physical video, physical lab, you will see me printing here, and exactly the same thing is happening in the virtual lab. So here I'm opening the build chamber to load the powder. Here I finished, and I'm closing the gas. So, and depurging is called the process depurging. See there, I'm loading the powder. Here the part is finished, and I will remove it. And that's what you do by yourself. So first you start with the gowning, health and safety. This is anti-static coverall and respirator. This is the printer here. You see it's very similar to the actual printer. These are instructions on the left, so the student see the instructions and do what is required. See, this is exactly what I'm doing here. And then, as I said, here the part is finished, and I'll remove it. You will see this lattice structure is also there. I will remove it. Here I'm loading the powder using the glove box, and I'm going to do the same over there. It's finished, actually. It was done. You're going of the video, so we finish just before the end, please. No, just the final part on the video. Start video. On it. Run the video. Go back. Run the video. Yeah. So put the cursor on it, the mouse, and go near it. Just to show the final. Escape the presentation. On the video from here. Yeah, on. Oh, it's not on. Okay. Can you show it on the screen? Yeah. Go near the end. Oh, yeah, here. And show it. Go back a little bit. We want to show this part. Back. Yeah. Yeah. If you can show it now. Yep. Anyway, just wanted to show you the final part when you take it from the build chamber. But this is the presentation, and I think, am I behind the time or zero? Thank you. So, go to the last slide, please. And any questions, I'm happy to answer, if you have any. Yes.
Thank you, Doctor, for a very nice presentation and informative presentation.
Thank you.
I'm interested in this technology, but I can see the limitation of the safety of this.
Yeah.
Of this. I think my question is, if I want to set up a lab,
yeah,
how much I need money?
This is
mean
actually,
for education purpose.
Yeah, very good question.
Yeah.
So you see this machine, the base price for this machine is 250k euro, 250,000 euros. That's the base price. But we bought options like 2 research facilities with it, which is the infrared, where I was showing the temperature profile. These are infrared sensors and camera, and the price went up to 350,000. This is German made. It's one of the best, but it's good in terms of research, not in industry. So companies buy something else, like GE, General Electric, or maybe like SOM. These are the make and manufacturers. But there are some suppliers and manufacturers from East Europe. The best event in the world on this technology is happening every year in Frankfurt called Form Next. I really encourage everyone, when you have the opportunity and the chance, go see it. You will find suppliers and manufacturers for everything you saw here, everything you need in this technology in additive manufacturing. It's in November every year in Frankfurt. You will find Chinese, Taiwan, Asian suppliers and manufacturers. From East Europe, you can get similar machine for 150K. Yeah, but you know the quality. So we've got this from Germany. It's very good. It's not too expensive and not too cheap. Yeah, that's only for the machine, but then you need like accessories with it. So if you have like 500K, 500,000, €500,000 or dollar, you can build very good lab.
Also, we need to set up a lab first.
Yes.
Special lab. Well, that's why.
Yes, because the air conditioning and aeration here need like special type of filter to isolate it from the HEPA 4 filter, which is standard. After that, when you filtrate it, you can even breathe. So you need to isolate this from the office. In terms of like protection from fire, also you need to have like gowning, changing area, and so on. Yeah.
Maybe separate,
Separate
building is better.
No, like we have it in the classroom buildings. We vent the outlet of the argon because we circulate argon. So we vent it to the roof, but it's going through HEPA 4 filter, as I said. Even if you vent it internally, doesn't matter. You will see like this event in Frankfurt, all the machines running in a room like this. The same machine, like some pharmaceutical industry companies use it internally. So they vent argon internally, but they only do some aeration to avoid suffocation and so on. Yeah, the consumption of the argon is not that much actually. When we start purging, we go up to 30 liters per minute. But then when we maintain, once we reach the purge level, we stabilize it for about 5 liters per minute. Yeah.
Dr. Mohammed, I have a question. The type of laser used is CO2 or fiber?
No, this is fiber laser and the YAG fiber laser.
With a kilowatt, how many?
200 watts. And as I said, it's replaceable, it's rack type. Now we are planning, actually, we have money.
Yes.
So we are going just to take it and put 1 kilowatt. This will give us like higher speed. So just to exceed the production.
Yes. When you talked about the surface roughness and the quality of the surface, and you said that post-process is needed.
Yeah.
So what type of post-process?
Polishing. So if your part is like strong enough, like you are producing, say, any heavy part that can take the abrasive, so you can polish it using any abrasive and traditional methods, like grinding, whatever you do to actual part to polish it. But if your part is thin, like lattice or Vistent or you cannot apply any force on it.
True.
So the number one option is the electrochemical polishing because of the complex geometry. So you immerse it in a container with acid and pass electric current. This will polish and take off the high peaks and make the surface more flat. Here what I show, I used CO2 laser for polishing. So we can use also laser, but the weakness with laser or the drawback with laser need external surfaces. So you can only polish the external because laser need clear access to internal cavities and internal features. So if it's a tube, you cannot polish inside, you can polish outside. So the other option will be electrochemical polishing. And there's like some other methods like injecting abrasive paste. It's a paste, a slurry paste with suspended diamond particles in it, and they inject it. I have actually videos on that I can show you later. And this can do internal cavities. Yeah.
Thank you very much, Dr. It's a very interesting research, really.
Appreciate it. Thank you.
you, Dr. Mohammed, for sharing such fascinating.
There's one more question. Can we take it or not?
Sorry for interrupting. So, thank you for this great presentation. It is a really interesting topic.
Glad to hear that.
Motivated one. So, my question is, what is the material you are using for printing? Yes.
Yeah, I show a combination of powder particles, metal powders. So far in our lab, we printed stainless steel, copper, aluminum, titanium, and Cornell. And Cornell is a nickel-based alloy, and the titanium alloys. So we printed these, but like I can say, almost most materials are metal alloys available for printing now. Like again, aluminum, copper, stainless steel, nickel-based, titanium. These are all printable.
Most of the material we can use to print.
Sorry?
But most of the material can we print it with, right? Most of the material.
Sorry?
Or most of the material.
Most material, yes.
Yeah.
Actually, they like.
Must be powder.
This is a very good question. Like as the technology progresses now, there are a lot of metal powders because the powder metallurgy technology exists from the 60s or the 50s. So powder metallurgy is there, but not all powders are printable.
Oh.
So you may see it's the same powder, but when you put it under the microscope, the geometry, it might be like elongated, like dendritic particles. These are a little bit difficult to deposit on the machine bed. The spherical powders are better. For example, nickel titanium and all titanium alloys, which have very wide application in biomedical and aerospace industries. These only came to additive manufacturing and being printable like shortly before COVID, during I think 2019. And proudly, I'm the first researcher printed nickel titanium in Ireland. That time it was just came to market, and we were starting our printer there in Ireland. So I printed. I have many publications on nickel titanium. You can check them.
Through the website, I see.
Yeah, the last slide, you can find my Google Scholar webpage. The first one was to optimize the input parameters with reference to the output measures, which were density, chemical composition, and so it was optimized during that research. Then I did another one to print it in pulse mode instead of continuous mode. Like in 3D printing, the laser is similar to electrical current. You can print in continuous or pulse mode. And I did the same. I also optimized the process to print in pulse mode. And then I reduced the energy density from 150 to 170 to get sound and significant results in nickel titanium down to 5 joule per cubic millimeter and get the same results in pulse mode.
Nice.
So you can find very interesting publications. And again, nickel titanium just came to technology 5 years ago, 6 years ago.
Very nice.
Yeah. Thank you very much. Thank you. Thank you. شكرا شباب. بارك الله.
Thank you, Dr. Mohammed, for sharing such fascinating insights into cutting-edge sustainable technologies and their real-world applications. Now, to honor our sponsor, Business International Group, may we call once again Dr. Malik Zakwani and Dr. Nasser Al-Haddabi, and also may we call the representative of BIG, Ms. Aisha Abdullah Al-Jahdami, to receive the certificate.
We now move on to our first set of online papers presentations. Each track will feature 6 presenters with 15 minutes allocated to their presentations. These sessions will take place here in the auditorium and will also be streamed live via Zoom. We kindly ask all presenters to be prepared and join their assigned breakout rooms on Zoom. To our audience, please settle in. We are about to begin the parallel sessions. Please scan the QR code on the screen to access the online session.